So yesterday we stopped at the discussion. The last thing I said, I repeated quickly so that we get connected to it yesterday again, is that all interpretations of quantum mechanics are incompatible with common sense, even though the best one, the Griffith and Omnes one, is incompatible because it leads to non-unity. So, but physicists, and so the problem is that when physicists claim that the Schrödinger or the Dirac equation are complete description of the behavior of particles, that must be wrong because they can only model a few particles, and so a few particles, the universe is not made of a few particles, so the equations can't be complete. And we will see in the next section that furthermore, the main theories of quantum physics contradict each other. So, and quantum physics is, I think, ontologically void. Basically, how is the theory of quantum physics created? So what is happening is that that there are very highly sophisticated machines, like the Stern-Gerlach apparatus, and these we make measurements with these, and then we have to use very abstract mathematics. Yeah, we need infinite Hilbert space. We need a dot product that is really complicated. This integral, very long integral that I've shown to you. It is basically, to fully understand, you need to have quite a track record of mathematics. So I just showed it to you somehow, but to fully understand, you need to go through many layers of mathematical education. And these are not the traditional experiments of classical physics, right? In classical physics, a good example, Newton's second law. Newton's second law is, of course, when there is no vacuum, Newton's second law is not right. So therefore, Newton developed his laws on the movement of the planets, whereas the planets are moving in a vacuum. So there it's really nice because you have quite a good system. But if you are here on Earth, you want to do an experiment with Newton's second law, you need to actually empty a cavity, make a vacuum in it, and then you can drop something. And then you really see the feather dropping like a stone. It's impressive. You can have a stone and a feather that drop at the same speed. That's then Newton's second law. So you need to adapt a bit the real reality to make the laws fit, but it works. So you can watch what's going on. This is a traditional experiment. Now the mesoscopic nature of reality is in these experiments reduced to a modeling environment. But that's okay. But now for quantum physics we have highly artificial and expensive settings. So and even so the Stern-Gerlach apparatus wasn't so expensive. But then when they started the high energy physics, the accelerators, I don't know what I'm not sure, but the Large Hadron Collider in the CERN, it must have cost 50 billion at least, or 100, I don't know, but it's really, really huge. These are projects if you think of the GDP, so Luxembourg is a bad example because it's the banking industry, but Northern Ireland, yeah, it's kind of in the annual GDP of Northern Ireland. So it's really, really huge what money this costs. And so these highly sophisticated systems are built to tease out data from very specific system situations. And so in this setting, what we do is we measure a certain aspect of nature, but we are scratching on the surface of nature, right? And we are getting then a very partial understanding of nature. However, it allows us to build quantum theory applications such as the laser, the transistor, the MRI, or quantum computers. And I mean the MRI, just the MRI on itself. So these highly specific models allow us to build quantum theory applications, but that does not teach us anything about the fundamental ontology of nature. It teaches us rather something about the nature of human epistemics, so how we get knowledge. And so a very strange philosopher, Giambattista Vico, he was a 17th and 18th century philosopher, typical Renaissance philosopher or Baroque times philosopher. His writings are very difficult to read because they are not systematic, but rather, you know him, right? You're Italian speaker, but he's a great philosopher nevertheless, because he was one of the first to understand that we can only understand really what we build ourselves. Now, for him, that has two meanings. Now you will certainly succeed. For him, this has two meanings. Build ourselves. So he thought that human beings can perfectly understand history because they make history themselves. We know that's wrong, and that's wrong because there are too many factors involved in the making of history. So the theories of historians are always very coarse-grained, but the activities of the human beings that do history are very fine-grained and difficult. So therefore we know that this is, but he was not right, but he also said, the other thing we do ourselves is technology. And at that time there was already very sophisticated technology which was being done. And so he believes that this technology, this technology, we can understand it perfectly. And he was right on this. Now with quantum mechanics, we see that we also generate knowledge of nature, but we do this by building first machines we understand well. With these machines we make experiments, and then we get results, and we build new machines based on these results. I call this the Vico plus circle. So because in the old Vico circle, what we did, it was not a circle, the old Vico was we do experiments on mesoscopic nature, we obtain results, and now we can build machines. But now we first build machines to obtain results to build other machines. So this, I call this Vico plus. So, and an example here of such a Vico plus machine is shown here on the slide. This is an old bubble chamber to detect particles in an accelerator. Right? So that's the only image I had on this slide, and later on it will be harder with showing the tables. But so the mathematical structures of essences we use in quantum physics do not give us any more ontology than common sense. So what is a structure of essence? So an essence is an a priori entity that we use in mathematics, like pi. So what are a priori entities? So the pi doesn't exist in reality. It's an a priori entity, and in the olden days it was called an essence. Now in the times where analytical philosophy dominates, Barry says I'm not allowed to call it like this anymore. I don't care here in this circle, I just say it. So an essence is so if you think of the universal tree, right? The universal tree, as it is in our mind, is of course an abstraction from all the individual real trees. But according to Aristotle, there's a universal instance relationship. Now you can think of pi like such a universal, but without instance. So that's why it's not universal, but an essence. And so for Plato, everything was an essence, and then all the individuals were just, so to speak, examples of the essence. Of course, I'm not a Platonist at all. Even when I was 15, I thought that this is nonsense. When I first read the dialogues in which Plato exposes these ideas, but I still believe that there are essences which are entities which are mind dependent, which only human brain can conceive of, and which don't have instances in nature. And that is mostly mathematics, but also topics like freedom, justice, eternal life, and so on. These are all, entities that these are non-universals. And so we have them in mathematics as well. And so what we can see is that the mathematics of quantum physics are beautiful, really. I mean, this whole way that Dirac and the others have set it up to build this Hilbert space, to model this, is very elegant. We can make very effective predictions, but they do not teach us more about the ontology of the world than common sense does. Yeah, because with common sense we have a very good understanding of the world and how we should behave in the world without hurting ourselves and still ensuring survival. And the whole classical mechanics, classical engineering is like this, right? It is basic. The whole classical mechanics, classical engineering is common sense based. And so quantum physics is a field that shows us the limits of our ability to model nature. Why is this so? So I'm not talking about statistical mechanics. So statistical mechanics, which is a part of thermodynamics, can model many particles, but not where the individual particle is, but it models distributions of particles. So it can model, for example, the carbon dioxide that was in this bottle. Hi there. There's not so much left in it now, but there is still a little bit. Let me see. Yeah, not enough anymore. Oh, that's also from Italy, as you see. And that it can model, but it can't model where each particle of the carbon dioxide is. It just can say how they are distributed. So, and then we have theory of complex systems, and there we learn also that, which is also part of classical physics, and there we also learn our limited ability to model nature. So for good physicists, it has always been clear that physics mostly models system situations that have been carefully prepared to enable a mathematical fit. So, for example, Kant himself, in the Kritik der Urteilskraft, critique of judgment, he describes that a blade of grass, if it grows, he says, certainly nobody will be able to show me how Newton's laws explain the growth of the blade. And so so Kant saw the limitations to complex systems, and and even, you know, good physicists always say yes, but we have to describe the system in the way that we need, so we prepare to be modeled by mathematical equations. So I gave you the example yesterday of the trajectory of the Earth around the Sun. It's not an ellipse on average. It's only an ellipse on average, but the Earth wobbles, right? It doesn't go around, but it goes around like this. It slightly wobbles. And that's due to the gravitational field of the neighboring planets. And quantum mechanics, however, drastically shows us the limits of mathematical models, because it results in models that can contradict common sense. And so I think the main benefit of mathematical modeling in physics is predicting for technical purposes. And that's why also physicists like Griffith stresses the utility criterion. You remember yesterday I showed you his 4 criteria, and the last one was utility. And that's what, and also Feynman says this, yeah. So that utility is the ultimate thing that is needed, and so, yes?
So I don't believe that the quantum mechanics models contradict common sense. They contradict the attempts to apply common sense in arenas where it is no longer claiming to be valid.
Yeah, but look, let's go back to what we said here. So these are the two alternatives summarized. So non-locality and holism contradict common sense, and non-unity also. it's just, and either is this the conclusion? This is 99% of physicists and mathematicians shows this today, and the others, and the non-unity
is a single particle, right?
Yeah.
By common sense, we mean primary theory in the sense of Holton. Primary theory doesn't talk about the very small, and it doesn't talk about the very large.
Yeah, but if you think about this from a perspective of common sense, you can't make sense out of it. It's just you can't make sense.
True.
So that's a contradiction.
No,
it is.
It's a misapplication.
But it's very easy to say. You can always talk yourself out of it, Barry, like this. But basically, if you want to have a view of the world that is coherent through and through, and then you look at quantum mechanics, it breaks this view.
I accept that.
So and that's what I mean. And so therefore we see that we see from this example that mathematics has this problem. And this was basically my main conclusion from yesterday's, from what I couldn't finish yesterday because I wanted to. It had already been more than enough yesterday, but now we can, before we move. So this is now comes my favorite part about particles. But before we move to it, because it's even more insane. But before we move to it, do you have any questions regarding or discussion needs regarding the last part?
Have you considered looking at people who have like the opposite almost view that you have?
Yeah, Tim Maudlin.
No, even more opposite, like anti-structural realists, like Asfeld and Vincent Lam and
yes.
Ladyman.
I just met Asfeld 2 or 3 weeks ago, and I said I met, yeah, that's what I said. I met I met him 2 or 3 weeks ago, and we concluded that he should do more mathematics. So I just think these people, all of them. Maudlin is different. I think he's a physicist and who does also physics. But if you look at, so there's a book by Asfeld, Philosophy of Physics, which I cite several times, and either the people writing this book are either physicists. If we go back to this diagram, so the people who write in this book, so are either here because they're physicists, and Asfeld, for example, believes in Bohm. So, but if you believe in Bohm, you should just do more mathematics.
To see that Bohm is wrong.
Yeah, because Bohm is incompatible with. So if you propose a model that is incompatible with theories that are based on many experiments, you have a big problem. So it's just inconsistent, right? And so you can understand if you read any textbook of quantum field theory, then you see that Bohm must be wrong. Because all the experiments we've done, even if they are only specialized settings and so on, they contradict him, and so it's actually even if you look at astronomy where they use spectral lines of helium or other atoms, you see that Bohm must be wrong. So it's just so basically, so yes, I've looked at the others, but I think that the two real alternatives are only this one and this one. This one I reject for philosophical and mathematical reasons. This one I accept, but it's still tough nut to swallow. But I wouldn't say that I've looked in every detail of every theory of quantum mechanics, but I think I've looked sufficiently so that my classification is correct.
And would you say that Bohm is now generally regarded as having been superseded?
In physics, by physicists, yes.
Yeah.
But the philosophers have this problem. So look, I now spent 1.5 years to learn physics, that I'm at this level that I can understand all of this. Now, I think, why shouldn't they do it? They're certainly intelligent enough as well, because they waste their time, you know. And right, so I mean, okay, I studied mathematics, so then you have a huge advantage of learning physics faster, but still physics is very weird. So it starts with it starts that all the time you feel that, wait a minute, but that can't be mathematically right. All the time they are bending mathematics to fit into it, and so it's kind of, but still you get used to it, right? Anyhow, so I think if you want to, as a philosopher, talk about physics and mathematics, you should study it yourself. And Frege did this, he was a mathematician before. Husserl did this, Russell did this, Wittgenstein.
Yeah.
Wittgenstein. So therefore, you know, you need to do it properly. Okay, now we have had all of this. Now let's go to particles. So this is so great. Oh yeah, sorry.
You might touch on this in particles, but yesterday you made some comments about noumena, just like, or maybe over the weekend.
Yeah.
That it's the weakest part of quantum theory. It seems like if you have this idea of non-unity or inconsistent models, it seems like that points to what Dr. Smith described like last week or 2 weeks in class about the, basically people think they have a Kantian view of quantum physics, that there's some weird wonky things going on behind the scenes that we can only describe in contradictory ways with these inconsistent models. And so like if we have non-unity, does that, like, how do we get rid of, if we have non-unity, how do we then still get rid of the idea of noumena?
So first of all, there are 2 ways of seeing the idea of the noumenon. There's the idea of the Anglo-Saxons, who hate Kant, like Barry does, and no, I'm joking. But there's the idea of seeing the noumenon as meaning that we can't understand how nature really is. Kant never says this. Kant says, to put it in modern terms, and I'm very certain of this interpretation, that we have a specific brain hardware that basically shapes how we see reality. And then he describes that animals have other brain hardware and they see it differently. So a bee has a different view of the world because the bee's neural system is totally different. So the bee has much more olfactory, the olfactory input is much more important. She can see different wavelengths than we, and so her view of the world looks really different. So you can go to the internet and watch videos that show you when the bee flies, how she sees the world. Or it approximates it a bit, but it's really fascinating. The same if you think of aliens who had a different evolution and now come to Earth. So they have, and so that's what Kant means. He doesn't mean that we can't see reality. He just says that there is so the noumenon just means, in my view, if you have a different brain hardware, you see the world differently. And so therefore I don't like the noumenon so much, but I don't think it's such a big problem as others. Now that's the first part of my answer. The second part of my answer is that when you look at quantum mechanics, there is no way out of that it is in contradiction with a holistic, common sense-based view, because it deviates from this view. Either you have the problem that you have non-locality and holism, which is terrible, which breaks physics itself. So that's why Einstein was right and rejected it. Or you have the non-unity which you obtain when you use the Omnis-Griffiths approach. Now, the Omnis-Griffiths approach is mathematically much more satisfying than anything else. It avoids this belief in non-locality. It avoids the belief in supraluminal signal propagation. So it's much better, but it still leaves us with the non-unity problem. So what does that mean? It just means that, and this is where Barry and I totally agree, that our whole cognitive apparatus, and that's also it's a biological argument, was shaped by the mesoscopic world. And so when we try to go beyond the mesoscopic world, we need to make approximations, and then we can't make sense of things anymore, because we are, I think, evolutionarily not adapted to the submesoscopic world, right? And so what we can do is, when we use microscopes, including electron microscopes, or, for example, single molecule tagging. So in biochemistry, we can tag a molecule, one molecule with one or very few molecules with radioactivity or luminescence, and then we can follow them, what they're doing. We can follow the molecules through an axon of a neuron, and if you use C. elegans as as a laboratory animal, we can watch this molecule in the microscope because C. elegans is a transparent animal, so you can shine light through it and see what's going on. It's great. I've seen people do. My colleague in the lab where I was a postdoc. He did this, and I looked through his microscope, his fluorescent microscope. It's so fascinating. You see, the exonic transport of neurotransmitter. So the neurotransmitter is made inside the cell, and then it's transported to the endpoint of the axon it's just to the synapse. It's brought to the synapse, and you can see then it's how to put out of the cell live. You see this in the living animal. But this is still mesoscopic in a sense that we don't have quantum effects yet because it's still too big, right? And only many orders of magnitudes below that we start to have quantum effects. And so with mesoscopic on the other hand goes quite far in the big stuff as well. So why am I saying this? Just to show you that whenever we can get a mesoscopic view of things, we are in accordance with common sense. And if we can't anymore, then we get phenomena that are difficult for us, but it has evolutionary reasons. It's a limitation of our cognitive capabilities, and it doesn't worry me. And the main reason why it doesn't worry me is that and that's why I'm so grateful that Barry pointed me to Omnis, because now I can really mathematically direct non-locality, and I can say, and I know which all physicists agree, also those who think of non-locality agree, that in the mesoscopic world all the quantum effects vanish. I have no quantum effects anymore, right? So even if the principle of creating a laser beam is based on the knowledge of quantum mechanics, the laser itself is not quantum. It's just a ray of light of uniform wavelength, right? And astonishingly perfect uniform wavelength. And that can be done, as I explained yesterday, or that was Saturday, using quantum theory. But then I have no quantum. I just have a very precise beam of light. I can use it to make perfect measurements and many other great things, light barriers and all the stuff you know. Okay, read CD-ROMs and so on. So I would say we move on to this because I want to bring you this chapter, and it's better if I explain it once. You can read it later, but I should explain. So, what is matter made of? So, Democritus, what's the English pronunciation? Democritus, thank you. Matter is made of indivisible atoms. Here I've put for you, I made it with latex, atomoi. So that's the Greek. So that temno means I cut, and tomos means cuttable. So and tomo is plural, so atomo is just uncuttable. The uncuttables, it actually means. and atoms constitute matter and give it its properties. And he already believed that there are different atoms. And so if different atoms are combined, different types of atoms, if they're combined, you get all the different properties of matter. And he said that atoms are unobservable. And that was, what it shows you is how far you can already get in Western thought without any experiment, because these guys didn't make any experiment. So, and that basically was until Lavoisier came. That's the guy who was executed in 1794. The revolution that needs no chemist, said the judge. He came up with and by the way, this shows you how bad it becomes when secondary theory, gets out of range. So that's what happened in France at the time, and so he developed the chemical element theory. Then these guys, how do you pronounce them? Dalton, Maxwell, Boltzmann, and Thomson said that atoms are not observable, and this theory was still based on metaphysical assumptions. Still until Thomson, right? It's quite impressive. Therefore, Ernst Mach in 1880. He rejected Ernst Mach, the genius. I mean, one of the greatest geniuses of the 19th century physics. He was. You have to read his books. I mean, his philosophical books are so great. He's a really great thinker, and he rejected the existence of atoms. He said, "No, we don't want any metaphysics. This is metaphysical. We have to get rid of it." So I read the passage. It's so funny, really. And anyhow, then Rutherford said that he made an experiment with gold particles, and from this very well, and from the measurements he could conclude. So before that, Thomson thought that basically the center of the atom is negative and the positive is spread out, And from the way that the experiment was, Rutherford concluded that the center of atoms contains the bulk of their mass, and he said that there's a protonic nucleus that has a positive charge.
And by negative, you mean negative charge?
Yeah. And then came the quantum mechanics led to a new model of the atom by Niels Bohr, Heisenberg, and Schrödinger. So Bohr was the only non-German in the whole group. He was a Danish guy. He was very clever, and he said that basically Bohr said the atom is made like this. So I have a positive charge here inside, and then I have electrons around this, and which have layers. Schalen, how is this called? Schale.
Skins or sheaths?
Shell it's called. Shells, and so the shells are the energy levels, and if an electron moves from one shell to another, then I get an energy, and that is the Planck constant times the velocity, and that's a photon that is going off then for the conservation of energy. Then we had quantum field theory. Feynman started quantum field theory in the 1950s, and then and now we know that quantum theory does not see protons and electrons as particles anymore, and it also has no classical fields anymore, and we will see what that means. So now all the particles are now smeared out in space, and the classic field, which is basically in which there are interaction between particles, doesn't exist anymore. But now field and particle have become the same thing, and it's called field quant.
But that picture on the right is still more or less correct, of these smeared particles.
No, yeah, I mean this picture, Bohr's model had to be revised, right? So Bohr's hydrogen model is pre-Schrödinger. So after the Schrödinger equation came out 10 years later, it was totally revised, and then we got this. I've only shown it to, that's I think helium, but then we get such models, which are much more complicated, which show, yeah, so that's the current atomic model of helium, calculated with the Schrödinger equation, predicting to incredible precision the numbers that are calculated here. So this was pre. The point is that you can't put this on a nice picture, the other one, that's why I put the one by Bohr, but it got outdated when the Schrödinger equation came out. So now in the common sense view, particles have a mereological and a causal significance. So particles, in a mereological sense, particles are parts. They are the microscopic components of the macroscopic material entities, like Democritus said it. So that's, for example, sodium chloride crystal, yeah. And so you see here how it is. That's actually not an impurity, but a different crystallization pattern. So this is how it really looks, more or less. And then there are also causes. So particles are not only parts, but they are also cause events. For example, the energy of particles causes the aggregate state of matter. So this is a video which I can't show now, but if if I'm at 0 Kelvin, these particles don't move, and then if I increase the temperature, they start to move, and if the temperature is high, they bounce around like crazy. If I make it still higher, the electrons become sheared off the nucleons, and then I have what I have in the sun, which we call plasma, which is basically only protons separated from the electrons.
And this is in the common sense view.
Yes.
And so this is all wrong.
No, let's see what does become. No, this is not wrong.
But we use this in our book.
What?
This theory of particles.
Yeah, but that's fine. It's not wrong. It's just a classic view. Now, quantum physics has no causal explanation for the stability of the atom, of the matter. That's very strange. So wow. I thought we just learned that quantum mechanics gives us an explanation of matter. What's wrong here? So the question is, look at this Bohr view. So why doesn't this electron is, of course, electrostatically attracted by the proton, right? The proton is positive, the electron is negative. It should just fall into it, right? Why doesn't this happen? Why doesn't the electron of the hydrogen atom fall into the nucleus despite the electrostatic force attracting electron and proton? Now, quantum mechanics says because of the Heisenberg uncertainty principle. Now we learned it, and they are the difference in location and momentum, and that's the Planck constant. And Feynman now says it's so funny. How this quote is so great. And I can't imitate Queen's Jewish accent, but so I have to read it out with my poor German accent. I'm sorry. The electrostatic forces pull the electrons as close to the nucleus as possible, but the electron is compelled to stay spread out in a distance given by the uncertainty principle. But of course, the uncertainty principle does not compel the electron. The uncertainty principle just describes it, but it's not the reason for this. If it were confined in too small a space, it would have a great uncertainty momentum, but that means it would have a high energy, which it would use to escape from the electrical attraction. So the electron, in the view of Feynman, calculates for itself the Heisenberg uncertainty relation, so to speak, and then it doesn't pick up momentum because it keeps its distance far enough. Yeah, otherwise it would use it. So this is complete nonsense. I mean, it is if you would have formulated it in a descriptive way, that the Heisenberg equation describes a behavior that we don't causally understand, the sentences would make total sense. But he here confuses causal explanation with description. Otherwise, so we have a description of matter, but we don't have a causal explanation. We don't know why matter is stable. We have to admit this. You were asking a question.
What page or like what lecture does that come from? Is that from volume 2?
That's volume 2, chapter 5. I gave the exact location because it's so curious. This means chapter 5, page 4. So Feynman has a strange numeration. So if you go to feynmanlectures.caltech.edu, or I mean, you just type Feynman and Caltech in Google, then you get there. Then you get to the table of, go to volume 2, and then all the chapters have, okay, they don't have the pagination. So if you have the printed edition, then the pagination is 5 minus 1, 5 minus 2, 5 minus 3, and so on. And online you can find it by just the electrostatic forces in chapter 5 in the search window, and then you get to this quote. So this is, so to summarize this, we have a great description of why matter is stable, which is the Heisenberg equation, but we have no causal explanation. We don't know why matter is stable. We have to admit it. Which I think is quite remarkable after all the billions we spent on high energy physics, but anyway.
So, the way I've understood the Heisenberg uncertainty principle is that it's a necessary uncertainty of any attempt to measure the behaviors of particles precisely.
No, it's also it's not only this. It's also it also means that the particle, given a certain distance. So if I want to know something about the momentum, I divide by this equation by x. Then if I make x smaller and smaller, this will just become bigger, and so then the electron would fly off. So if I would, by approaching, theoretically, if I now approach the proton more and more and more, this becomes smaller and smaller, far below 1. We are now at 10 minus 29, 10 minus 30 meters. And so this explodes, and suddenly the electron has many electron volts, so many that this would become a plasma. That's what he's saying.
Why is it called the uncertainty principle? Why not call it the anti-gravity principle?
Because there's nothing to do with gravity.
Well, the anti-force principle.
Oh, because it's the uncertainty principle. This is just one pair so this is a pair of two uncertainty principle magnitudes, but you can also put spin up, spin down, or many others. So the uncertainty principle applies to many properties of quantum particles. So it's not.
Is there any explanation for that?
Yeah, we saw the slit. I mean,
okay.
we saw the slit explanation that is used to explain that Feynman uses. Nobody has any better explanation. You can see how it's derived by using the slit, but you can't. We don't know why it exists, right? So we just have to stand there and accept it. Yeah. There was a question somewhere.
Yes, and just to clarify the last sentence. So when you say the inequality is merely a descriptive law, I wonder if you mean all the inequalities and equalities in physics are all descriptive
So this
or some of the inequalities and inequalities in physics are more than this.
Yeah, some are more.
The causal explanation. Can you give some examples on how to do that?
Yes. So first of all, there are many. So the law there are two types of laws in physics. There are causal. There are the so-called laws of nature, which are called causal laws by physicists, and then there are the phenomenological laws. Phenomenological laws are laws which are created from so-called causal laws. So F equals m times a, Newton's second law is called causal law, because it's supposed to describe a causal relationship that exists in nature, right? And now we won't speak about causality today. It's a huge topic. Yeah? But now today, Mach gave up the notion of causality. So Mach says there's only this. So instead of causality, he speaks of function. So he says, I'm not writing f equals m a. I'm only writing f equals m times the derivative of velocity. So, and I prefer instead of f to also write on the other side another expression of force, so that I always have a full differential equation with a function on one side and a differentiation of a function on the other side. And now I'm only talking about funktionale Zusammenhänge. That's what?
Functional connections.
Yeah, functional connections. And I give up causality because causality is so metaphysical that leave me alone with causality, he basically says. So, and that was a huge trend. It's now, actually, it was so strong among physicists that even today, almost all physicists refuse to talk about causality. So what was a causal law before Ernst Mach is now functional relationship. So, and then we have still the other two, descriptive and predictive. Now, descriptive is when you can using, descriptive laws when you have something in nature that you don't understand why it is so, but you can describe it well, then you have something like this. And when you have a predictive law, it's a Schrödinger equation. It's a highly predictive law, and it's also, it used to be called, before Ernst Mach, it would have been called a causal law, but now it's called a functional law and a predictive law, and also descriptive. So it's all three, right? And an example of an inequality that is predictive, yes. So for example, v smaller equal c. Every velocity in the world is smaller or equal the velocity of light. And if it is actually equal, then it must be an electromagnetic wave traveling in a vacuum without restraints. So this is, for example, this is descriptive and also predictive, right? Because it allows you to predict many, I mean, a lot of physics is based on this inequality. And this can also be seen in a way as predictive, but it's not a causal law. And are there still causal laws? That depends how you see causality, right? So yeah. So and I wanted to talk about this, but then I would have had to have more space in this course. Did you do causality in the course?
No, I was just going to make a remark for those people who know about BFO, that BFO does not talk about causality. Not because BFO denies that there is causality, but because there is just no good general account of what causality is. And so we just leave that question open until we can work out what the appropriate way of treating causality.
Basically, causality, so if we review causality, in our common sense we have causality all the time. That's basically how we survive. In physics has given up causality. Mathematics never had causality, so mathematics is causality free. And so causality is in common sense, and in the humanities it's very strong, and in physics it has been kind of rooted out. But if you, in philosophy, physics, of course, there's still a huge debate on causality. That's all I can say here.
And common sense uses causality, but it uses it in so many different ways that there is no way of getting it.
Yeah, but what we have to accept, I think, for certain, and that you can see this already in Aristotle, causality is a metaphysical category for sure, right? And it will always remain like this. I'm pretty certain. So now, quantum field theory is used to derive the standard model of elementary particles, although it has no real causal account of what matter is. So what's the standard model of elementary particles? Let's take a look. So we have here the fermions. These are the particles that make up. It's not, the resolution is not good, but I will tell you a bit. Which make up matter. They have spin 1/2, and then we have bosons which have spin 1. So these are the particles that make up matter. Those which we can discuss here a bit are these. We have the electron. Well, it's almost unreadable here, so I try to read it. So we have the electron, then the muon, the tau, the electron neutrino, the meson, and the tau neutrino. These are leptons, and then there are quarks, and the quarks together they make the they make the hadrons, so they make the protons and the neutrons. And then we have the bosons, which are the particles via which the others interact. So gluons is the interaction particle of quarks. Photon is the interaction particle of electromagnetism and electrons, and then bosons, Z and W bosons are intermediate to weak force. Bosons, gluons, the strong force, and the electromagnetic force is mediated by photons. And and the leptons interact via the weak or the electromagnetic force. And so this is basically these are the particles, and we have all this, and we will see a bit later that they are classified by algebraic group theory. So now we don't classify particles anymore via very many experimental properties, but only a few experimental properties that we can use to create algebraic groups, and we will see this in a bit what that means. Okay, now quantum field theory is an extension of quantum mechanics to deal with systems involving many particles and relativity. So let's look at this. This is quite an interesting diagram. It's taken from the Stanford Encyclopedia of Philosophy, Entry Quantum Field Theory. So we have classical mechanics, and if we now move from classical mechanics to quantization, we get quantum mechanics. So if we move from classical mechanics, a few particles, to an infinite amount of particles, we get classical field theory. So in a way, you can already see non-relativistic classical, so thermodynamics can be seen as a non-relativistic classical field theory. Now if we take special relativistic field theory, we can get relativistic classical field theory, for example, classical electrodynamics. If we add quantization, non-relativistic classical field theory, we get non-relativistic quantum field theory, and if we then add relativistic theory, we get relativistic quantum field theory, which is, so to speak, the highest theory we have today. So where is here quantum electrodynamics? Quantum electrodynamics is not shown, but it would be classical mechanics with quantization and relativistic theory. So here, so to speak, if you invert the two, then you would find here. So it's not shown here. So here it only occurs because this view is a kind of schematic. So but if you take quantum mechanics and now add special theory of relativity, then you would have here quantum electrodynamics. So quantum field theory is an extension of quantum mechanics to deal with systems involving many particles, especially fields which cannot be modeled in classical quantum mechanics. Quantum field theory became necessary to interpret high-energy experiments which deal with relativistic effects, which classical quantum mechanics cannot take into account. So the Schrödinger equation is not Lorentz invariant, right? And so you need the Dirac equation, and then it becomes. Note that the schema does not show quantum electrodynamics, as I mentioned. Yeah? So it's quantum mechanics of a few particles combined with special theory of relativity. Now we will see that the evolution to quantum field theory leaves no room for particles as the smallest elements of matter anymore. So instead of this, we have only mathematical group theory left. Now this is why we need the projector today. And thanks again for setting it up. So you see here, this is now the different. So this gives you an overview of the different particle theories in physics, and I think we have enough time to cover all of them and to leave you puzzled and at the end of this day. So here's the classical physics and here's the quantum physics. Both share an operation of your particles, which is really attractive, which we'll see in a minute. Then we have quantum mechanics, quantum electrodynamics, and quantum field theory. And these are direct theories in the sense that they are directly derived from observations, all of them. Field theory is only half derived from observations. It's already in between. And then we have derived theories, which are mathematical improvements of what is there above. So it's group theory, virtual particles, and quasi-particles. And we will see all of them and how this all hangs together. Not hangs together, but it's very interesting to see. So let's start with classical particles, and we will use these abbreviations all the time through to compare the theories. So the tables will become, there will be more and more properties, and it will become more and more difficult, but it's really funny. So let's start with classical particles. So they have the property of having mass and charge. So Q is the symbol for charge in electrostatic theory or electrodynamics theory. They have dynamic properties such as mass and charge. They are independent of each other, then they can be non-interacting and are statistically uncorrelated. So each particle is uncorrelated to the other, and they can be non-interacting. there are points with mass. So what in hell is a point with mass? Right, in mathematics a point is infinitely small. So in mathematics a point, therefore a circle has an infinite amount of points because it's infinitely small. So but in physics it's a point with mass. Democritus was the first to describe it, and Newton and Einstein agree that particles are points with mass. Then they are subject to the conservation of energy, momentum, and angular momentum. So not only so all of this is conserved in the classical view of physics. They have trajectories determined by the laws of classical mechanics. We have seen the pictures of the trajectories or world lines. They have also trajectories described in a phase space, which allows the computation of their location and momentum at every time point given initial conditions. That's the world line. They can be separated to the individual level via measurement of their world lines. So like if I have, for example, two cannonballs shot by two cannons at the same time, they have different world lines. I can measure a segment of each world line and predict their location. That's actually what the self-defending anti-missile systems, modern systems do. Right? They measure 2 points on the trajectory, and then they can determine the entire world line and then do this. They can be separated to the individual level via measurement of their world lines. They are located, so they can be individualized. They are localizable at every point, and they can form bound systems, which is, all of this is totally in harmony with common sense. And that is basically what Einstein found when he started to do physics, that view. And what is so nice, Einstein hasn't changed this, right? He has made a theory that still keeps this in a way. That's why what Einstein did was incredibly difficult to do, but still much closer to our common sense than what the others did. Now, we cannot measure real particle trajectories using an accelerator plus detector. So if you have an accelerator, the electron or proton gets accelerated, then it enters a chamber to measure its trajectory. In this trajectory, how these chambers work is that they ionize a gas, so the accelerated particle knocks off, for example, electrons of other particles that are in the chamber. It's usually gas. So that's a bubble chamber. That's a bubble chamber. That's the right term. But bubble chambers are not used now anymore. Today we have wire chambers. I just wanted to avoid to say gas chambers. But the point is that the chambers are filled with gas, and the gas, and it's very carefully mixed of gas. And so when the particle with the high acceleration enters, it knocks off an electron from the nucleus. So the atom becomes ionized, it becomes positively charged, and then it's attracted to the wire. The wire is charged negatively, the proton hits the wire, and there are so many wires that when you measure, and when the proton hits the wire, the current is changed. Yeah, because some of the electrons in the wire get neutralized, so you have less current, you have a drop in the current, and you can measure this drop, and if you measure all the drops in all the wires, in nanoseconds timing, you can recalculate the trajectories. But you cannot measure the trajectories directly. What you measure is how they knock off electrons from other atoms, and that's very important, because when they knock them off, they also change a bit their trajectories, right? They lose momentum, because, I mean, if they knock off an electron, they will not lose much momentum. A proton knocking off an electron is so much more heavy, but still, so you get, and then what you get are basically in the bubble chamber. If you zoom in, you don't get a trajectory, but you get single bubbles. Each time the particle on its trajectory hits off, so it's a wave, an accelerated wave, right, from quantum mechanical perspective, and on its way through the chamber, it will create, to put it in von Neumann's terms, wave function breakdowns, and each wave function breakdown is, so to speak, then a measurement result. And so what they do is when they calculate the trajectories, which are not real trajectories but series of dischargements of proton of cations, yeah, then they use classical Lorentz force. So this is classical physics. Although we are here to have a quantum effect, they just use, they have no choice, they have to use the classical Lorentz force. Then, which basically says this is the charge of the particle times the electric field plus the charge of the particle times its velocity, cross product with the magnetic field. But from a quantum mechanical perspective, we cannot measure classical particle trajectories. At high resolutions, it becomes clear that the trajectories are a series of separable measurement points, which is an essential result following from the underdetermination of quantum physics with regard to location and momentum. What we measure in the detectors are subatomic scattering events. A scattering is when the electron gets knocked off. So this is first of all to make clear what we measure. We are already in the middle of the quantum conundrum when we do the measurements in high energy physics. Now, therefore today's operational description for particles for measurement purposes is so restricted because they can't say more because it's so little that we can still say. So yes, now a particle from the operational view, and to remind you, now you understand why I've put operational here. And this is from me, this is not from the text. I'm quoting a text, but I made this myself. So because classical and quantum overlaps in the operational description. So a particle is now a bundle of dynamic properties such as mass, energy, spin, and charge. But it's only a bundle. It doesn't have the properties anymore. It's just a property bundle. It's approximatively localizable using detectors, but not really, you see, because you have only these collision events. And it's statistically uncorrelated with other particles. So of all you saw a long list of properties of classical mechanics, that's only what's left, because operational physics can't do more. It does not assume anything about the nature of the particles between measurement events. So it can't, between the two bundles, well, it's a wave, right? But a wave, we are talking particles here, so it's almost nothing in between. It only uses the causal nature of particles, so they are not parts of anything anymore. Now we concentrate on the causal nature. You remember the part is a part of something. It also has a cause effect. Here it's only causal. From this perspective, it's not clear what holds the properties to the bundle together. They are just, we can measure them, but we are not, what holds them together we don't know. It distinguishes many types of particles, so it's actually perfect positivism. Yeah, so if you say, give me an example of applied positivism in physics, that's this definition of a particle. Yeah? And we don't know what holds it together. It's really what the Vienna Circle wanted to do, get rid of metaphysics. Here they've done it. You can see it almost perfectly. I should write this the next time. Particle physics distinguishes many types of particles today, which are characteristicized by their trajectories and interactions, and quarks are dot line centers of scattering in nucleons. So that's another side. Yeah. So, but this is straight from Perkins' high energy physics. It's a standard textbook of high energy physics.
Yeah, they need help.
Yes. So quantum mechanics and classical physics can only overlap with regard to a minority of practical particle properties. So now we see already the big conundrum. So here now I start this is what I promised to now start to compare the properties. So that's mass and charge in the classical view. That's not quantum mechanics. So the particles have dynamic properties such as mass, charge, and spin 1/2. Why only spin 1/2? Because quantum mechanics only talks about spin 1/2 particles. Quantum mechanics doesn't talk about photons. They are independent of each other, but here in quantum mechanics, particles are waves. They are only points upon interaction. Yeah, so that's, to repeat it once more, that is not von Neumann's view, but that is Georgia Penrose's view, who says the function breaks down all the time when particles interact. They are subject to the conservation of energy, momentum, angular momentum, and spin, so that's good. But here in quantum mechanics, particles only obey the probabilistic law formulated in the Schrödinger equation. They are in a wave state defined in the Hilbert space and interfere with each other as waves. We have seen this in the double slit experiment.
So, but you say that they break down.
I'm not saying this.
Okay.
No, I'm portraying the view of quantum mechanics.
They can't have their cake and eat it. They say they're points only upon interaction.
Yeah.
But then you say that when they interfere with each other, they're waves. Those two lines are
Yeah. I know, but interaction is not interference.
Okay.
That's important. So when you have a double slit experiment,
Yeah.
and you shoot with this electron cannon, then you are not creating interactions, but you're creating interference.
Okay.
That's really physically different. Now they cannot be individuated via world lines in space-time. So that's very important. So you can't anymore have a world line. This is what Tom was puzzled about yesterday, because Tom is a classical mechanics and quantum theory, general theory of relativity type of person. Like all engineers, he's an engineer, and so he doesn't want to abandon the world line. Yeah? And like Einstein. And so we have two aspects. We have the Heisenberg uncertainty, and we have the Pauli principle that particles are exchangeable and only determinable by quantum state. So the two electrons, which are in the helium atom, for example, we can't distinguish them, right? Unless we have another atom that has more shells. Now the outer shells have more energy, And now those which are on the outer shell, we can distinguish them, but on those on one shell, so we can distinguish the outer from the inner shell, but those which are the same shell are indistinguishable.
But you said that the shell view was not.
No, shell view is correct, but
Earlier you said it was not.
no, I just said the Bohr view was too undifferentiated. The shell model, then I showed briefly the helium shell model, which is still with shells, but much more complicated. But the shell model is indeed right, but not in the way that Bohr thought, because Bohr had no equation. So when Bohr wrote it down, it was a hypothesis. And then when Schrödinger came, they could transform the hypothesis to a real theory. Now, they are not localizable at every time point in space-time, so which is extreme. They are approximately localizable using detectors, but still, that's good. They can still form bound systems. Okay, so now we see how quantum mechanics changes the view of particles and how few only of the original properties are left. Now we come to quantum electrodynamics. Oh God, yet another view. So now particles can have energy but no mass and charge, and their spin is 1. So these are photons, right? Quantum electrodynamics is a theory of photons. So they have no energy, but they have energy but no mass and charge. Their spin is 1. They are totally independent of each other. That's good. That is conserved. They are point-like mediators of electromagnetic interactions. So they are not anymore point-like mass bearers, but point-like mediators of electromagnetic interactions. They are subject to the conservation of energy and spin. That's good. They only obey the probabilistic laws formulated by the Maxwell equations. Wait a minute, what? So now we have, and that's the Dirac equation. The Dirac equation basically says that they obey probabilistic laws formulated. It's a probabilistic view of the Maxwell equations. They are in a wave state defined in the Hilbert space via phases phi or occupation number n and interfere with each other. So occupation number is a term from quantum electrodynamics, which we haven't had. We can't go there, but that's what the definition is. So they are also in a wave state like in quantum mechanics. They cannot be individualized via world lines in space-time. And they are and here now we don't have the Pauli anymore postulate, but we have the Bose postulate. They are principle. They are exchangeable and not discernible, right? So that's even stronger than Pauli. Pauli says they are exchangeable and only determined by quantum states. So we can measure the quantum state. So for example, in the helium atom, one of the electrons is spin up, the other spin down. So we can, at the end, if we measure their spins, we can determine, again, know them, that we have one with spin up and spin down. But Bose says they are not even discernible, and so that means that it's even worse, right?
How could you know that they're exchanged if you can't discern them?
Yeah, I mean it means that you can. It's just the anonymous mass of particles, or every particle has the same. It's the same.
Okay.
You can't say this is this one, this is this one. There's nothing to, and that Bose, that's why they're called bosons, because Bose was the first one to show this mathematically.
But an anonymous mass of particles is different from a single smeared particle.
Yeah, because you have more than one. Then you have a lot of
Each
smear.
one of them might be. Are photons smeared?
They're waves. Of course they're smeared. They are not localizable at every time point, but are approximately localizable in detectors. So if you can have a photon detector, and then you can give an approximative localization. Now comes the bitter pill. They cannot form bound systems anymore, right? So because they have no mass. So now you have lost the bound system property. Now comes quantum field theory, which is even worse. So you see the table is getting broader and broader, and less properties are in common. So quantum field theory says that particles have dynamic properties such as mass, charge, and spin, and they can be fermions or bosons. So that's nice in quantum field theory. Again, here in quantum electrodynamics, in quantum mechanics, the one is about particles, the one is about photons. Now, hooray, we have finally again a theory in which they can both be in one theory. That seems like a progress. Or does it? Because now, okay, they're still independent of each other. They are point-like with regard to interactions. Okay, that's like in classical quantum mechanics. They are subject to the conservation of energy, charge, spin, and other magnitudes. they only obey, so that's also good, they only obey the probabilistic laws formulated by quantum field equations. Now we have different equations. We don't have the Schrödinger equation anymore, we don't have the Dirac equation anymore, we have now quantum field equations, and they obey those probabilistic laws. They are in wave states defined by the wave function and interfere. The amplitude of the waves are field operators. So now the old amplitude that we had, you remember the amplitude that we have in quantum mechanics, a cat, this thing here. Now we don't have amplitudes anymore defined by cat, which is nothing but a product of a complex, which is in the end a complex number, which we get from the exponential function, or from two exponential functions depending on the context. But now we have field operators which define the amplitude. They are indiscernible. They are not localizable at every time point. They are approximately localizable using detectors. And now some fermions can form bound systems, others bosons cannot.
So people and tables and planets are bound systems, right?
Yeah.
So it's good that we have those.
That we have
We have fermions because they make matter.
Yeah, so we have two theories that think that particles can form bound systems. That this is classical mechanics and quantum mechanics. Then we have a theory that cannot say this is quantum electrodynamics. And then we have an excess theory that says some particles can, some particles cannot form bound matter.
But that's a pretty stable result that fermions are the particles.
Yeah, that's very stable result.
Do you want to say a little bit about Frau Falkenberg?
Why? That's all from her, right? So she's really, it's very interesting. So one of my favorite philosophers, Arnold Gehlen, a German philosopher, once wrote that that there are very few women who get it, but they are those who really get it. So he as an example, uses this historian, I don't remember her name, I gave you her book about the 17th century Civil War history. She's very good, but at the moment I can't remember her name. And so what she writes about the Civil War in England is so brilliant. And he uses it as an example of a woman, and the other example would be Edith Stein, right? And there are very few. He on purpose.
Edith Stein, yes.
Yeah, on purpose he does not mention. He didn't like Hannah Arendt, obviously, because she wasn't. And so Falkenberg is a German theoretician of physics who is really good and who has put this together. I don't know her personally. I know Esfeld, but I don't know her. Maybe I will meet her later. And another one, I think the best is Nancy Cartwright. I think Nancy Cartwright is among all, since there is philosophy of physics in the modern sense, which is since the quantum mechanics was started, Nancy Cartwright, her book, How the Laws of Nature Lie, How the Laws of Physics Lie, is a collection of papers, but they are fantastic, really. And thank you, Barry, again for pointing me to her. And
then the title is a pun. So lie means telling lies, but lie also means determining the posture, as it were.
The operational properties of particles are shared among theories, but they differ how they describe particle interactions. That's very important. So in the operational view, right, we have that particles are bundles of dynamic properties such as mass, energy, spin, and charge. And here we have in quantum field theory, particles are bundles of dynamic properties such as mass, energy, spin, and charge. Barry would say not bundles, but carriers, you would probably say. Yeah? Now, they only agree with regard to what can be measured. That's it. But here in the interaction, so operational theory believes that particles are approximately localizable using detectors, and dynamic view says they are point-like with regard to interactions. Yeah, but operational theory doesn't say that they are point-like. Here they are statistically uncorrelated, and here they are subject to the conservation of energy, charge, spin, and other magnitudes. So the dynamic view explains what maintains the bundles of properties that can be localized as particles. So why do they speak of bundles? Because you need always you need each time another setup of experiment to measure another property, Barry, or very often, yeah. So that's why you can't measure spin and localization with the same machine.
They're not bundles.
Yeah, but they call them. Yes, I know, but they call them bundles because you can't measure the properties at the same time. You need another experimental setup.
Yeah, of course not.
And yeah, well, of course not. No, sorry. But it's very easy to say, of course, but it was normal to measure all the properties in one experiment for a long time. So of course,
measure them all at once doesn't mean that they somehow become
I know.
ontologically separate.
I know. We for us it's clear, but that's why they call them bundles, because they want to express that they cannot measure them together. And so the dynamic theory explains why they are still entities in a way. Yeah. Classical mechanics, these are trajectories in space-time, and quantum mechanics wave functions with a probabilistic interpretation. Quantum field theory gets rid of the difference between particle and field. So as a consequence, theoretical physics has derived an overarching particle concept based on the laws of conservation and symmetries, but not anymore a particle as we knew it in classical physics or also in a way in quantum mechanics. So now we have just a field quant. And the field quant is a smear, right? It's just the probability of being localized somewhere, having some other property, but it's not anymore. There is no particle. The particle and the field are now one. So a field is a set, or set is the wrong word, but a field is a collection, which finite or infinite, it depends on what system you're looking at, of field quants. So for Newton, I have two bodies, and they have a gravitational field, and now the bodies attract each other in the gravitational field. In quantum fields, you have only field quants, right? And then I have forces, which are properties of the field quants. So this is tough. So they have, and now comes a neglected genius. Sometimes they are neglected geniuses. This one here, he had another German, Eugen Wigner. So what he did, he said, we see this now.
What about experimental confirmation?
Yeah, we'll come to this. So basically what this guy, he saw already as a PhD student, he was a PhD student with Hilbert. Hilbert is one of the greatest geniuses of mathematics of all times. But Hilbert was getting tired, and this guy noticed, he was in his mid-20s, that he had conflicts with Hilbert because Hilbert was for him too slow, and he thought Hilbert is not creative anymore. But he felt very early on in 27, 28 that the big problem would arise with quantum mechanics, because of the dual nature of wave and particle, and the big issues with non-local effects. All this was discussed early on, right? And there was huge trouble in the physics community. And he saw this, and then he said his solution was that he said, we are now making a theory of particles that is based on mathematical properties. And so he says particles are bundles of dynamic properties such as mass, energy, spin, and charge. They are subject to the conservation of energy, charge, spin, and other magnitudes. They are described by non-coupled field equations for free fields. They are statistically uncorrelated and dynamically free of interactions, and now they can be described as symmetry groups. So all the particles that I've thrown in the table, each entry in the table is a symmetry group, an algebraic symmetry group. And the solutions to the field equations can be classified into invariance groups within group theory. These groups correspond to the laws of conservation of energy. Their classification is theory overarching and can be applied to quantum as well as classical theories. The quark theory is an example of it, but it can only see the particle as independent, isolated entity and cannot explain how matter is formed. So each group theoretical classification sees the particle as certain group properties, but there is not anymore an explanation of matter as formed. Only the first property, mass, energy, spin, and charge, is bound to experimental physics in which repeated measurements must be done to yield results. However, particles are only types, not individuals. There is no single field quantum, no particle anymore in group theory. So really a particle is only a type without an individual. So it's a mathematical entity. And so the only thing that still binds this theory to reality is this, that they still have an account of the measurements. And if I talk about the particles in a field, I don't talk about particles, I talk about field quanta, which behave according to the group to which they belong. So that's it. So I don't have, so it is very strange. Yeah, and it's very detached from so there is basically the single field quantum is only a type. So it's not an individual, and that's very, very strange. And I can't do more on this because I knew it would also be too much for this lecture. That was not his result in the late 20s. That's the result of the 60s.
But is this this still alive? Is
That's the standard. That's the most mainstream. So if you buy a quantum field theory book, that's what it says. So that's quantum field theory. So that was so quantum field theory. If you look at it, the 3 volumes standard work on quantum field theory has volume 1 is Introduction to Quantum Field Theory, volume 2 is Applications, and volume 3 is Symmetries. And volume 3 then, so to speak, contains all the mathematical apparatus to explain how the symmetries lead to the standard model of particles. The standard model of particles is not a standard model of particles, it's a standard model of quanta. So, and these quanta are the entries in the table that we use.
fermions are still surviving in this sense?
Yeah, they are a symmetry group. And their symmetry is that they all have spin 1/2. But then the different types of fermions have more properties which specialize them, and but for example, the electron is a field quant, and it's only a type. So so this is what I mean by derived. Now mathematically it's very beautiful, but it's strange. Now it gets worse. So what does it mean? So the operational view of particles describes their causal nature. The group theory renders their mereological properties. So this says that particles. Why is this a causal nature? Look at here. So because the operational view says that I can measure them, right? Talks about if I can measure something, detect something, that means I have causation. And group theory describes the mereological properties of particle types. So here, look at this. So we have this. So this here, these are all mereological properties. So this is the energy, and then there are different other, the charge, their spin, their color, and these are these groups that are formed here, like the groups 1, 2, and 3, and then these groups on the horizon are all group theoretical constructs. So this describes them as groups according to their physical properties, which we can measure, but it doesn't talk about their causal natures. So I'm going to continue to now we have seen group theory a bit at least, and now we go next in our schema. Now we need to go look at virtual particles. They are even worse. So virtual particles in quantum field theory. So quantum field theory needs virtual particles in order to compute the interactions between particles, which the Feynman diagrams show in perturbation theory. So here you see that is Rutherford scattering. So 2 electrons get scattered, and then they come here, they meet here, and then they move on different trajectories. That's electron scattering. That's one of the simplest Feynman diagrams. And this particle cannot be measured, this photon, but it's needed so that the equation that explains the scattering is mathematically valid. So these particles cannot be localized or measured, but their contribution to the interactions cannot be disregarded mathematically. They're needed to make the equations work. They violate the law of conservation of energy and only act in groups. So why do they violate the law of the conservation of energy? Because those 2 electrons still have the same energy they had before, but the particle appeared, but that can't be, because the particle has energy. But then it would take energy away from the 2 electrons, but the 2 electrons have the full energy. They're just doing this. So like in billiard, pool, how do you call this game? Pool? Yeah. So so that's what they're doing. Just one ball is hitting the others, and then they go off in 2 different directions. And so their energy is conserved, but here you need this particle in the equation that describes the interaction, but it has no energy, but the photon must have energy. So they must be there so that the mathematics work. But they violate the laws of conservation of energy and only act in groups. So only act in groups is they only appear when something else is happening. So what are they, these virtual particles? Well, they are abundance of dynamic properties such as mass, energy, spin, polarity, and charge. They are perturbative entities which contribute to the perturbation theoretical development of a scattering matrix. So the scattering matrix is needed, goes into this equation like the Hamiltonian we saw earlier on. The Hamiltonian matrix with the energy that we saw all the time in quantum mechanics. Here we now have a scattering matrix, which is also a matrix which is an operator that goes into the equation, and they occupy columns in the scattering matrix. If you take the columns out of the scattering matrix and then multiply the operator into the equation breaks. So you need them. They are in interfering and superposition states described by propagators in waveform. They are not statistically uncorrelated and diametrically free of interactions, but part of interactions. They are neither local nor localizable using detectors. They violate the laws of conservation of energy during the interaction. So you see that quantum field theory is broken in itself. Like, as a mathematician, I think that quantum mechanics for real-world systems with infinite Hilbert space is also broken because it requires the Dirac function, which is mathematically impossible. That's even worse because now I not only have an impossible function, but now I have impossible particles, because a particle that violates the law of conservation of energy during the interaction, that is basically, and that cannot be there, but must be there so that my equation works. Otherwise, the whole quantum field theory breaks down. So, and this is very, very bad, right? But this is the best we can currently do.
So what would Griffiths and Omnes say about this?
They don't deal with quantum field theory at all. So they have nothing, they haven't published
Why
about it.
should anybody deal with quantum field theory?
Because it is now the latest, that is because of this. Because without quantum field theory we would not have any of this. We couldn't have quarks. Quantum field theory is the only way to talk about quarks. And also the Higgs boson, all of these, the photon, so this, and this, all these bosons, with the exception of the photon, cannot be defined without quantum field theory. The lifetime of this thing is 10 to the minus 27, 10 to the minus 30, and of this one is even shorter, I think.
I really just want to save the fermions. I'm not so bothered about
Yeah, but then without the fermions, without bosons there is no proton, because a proton consists of quarks held together by the gluon. If you have no gluon, you have no quark, you have no proton. So then you are back to the atom. Yeah? Like, I prefer Democritus now, really sincerely. So I always thought Democritus was quite clever. Now I think I prefer him much more, even because at least this is all consistent. But I mean, here quantum field theory, that you need to have particles that can't exist, like Michael Endes' land that may not exist, if you remember it, right? So that's quite severe philosophically. So Falkenburg is really desperate about it. She writes, guys, we need to realize how bad that is. I'm shocked, and so on. She gets quite emotional in her philosophical text. Now it can get even worse. So let's look at, we are here now in our nightmare trip. We have now seen loops here in Virtual Park. Now we have quasi-particles, and then we are done. So what are quasi-particles? So in certain solid states, groups of particles behave like one single particle. So we will see a little later, if we get the time, Cooper pairs. There are pairs of electrons which behave like a single boson and enable the superconductivity property. So when we have superconductors, we have paired electrons who behave like a boson. So they both have spin 1/2. Together they have kind of spin 1. They act like one boson, but they are not one boson. But they become like a boson at the low temperature. Without that, we wouldn't have we would not have a superconductivity. So the magnetic resonance imaging wouldn't work without this Josephson effect, it's called. Other examples are electron holes in metals which can move in them and act like positively charged particles. So a transistor. So there are NPN and PNP transistors. In a PNP transistor, so there are three metals put to three materials next to each other, and then you know that the electrons move through them, but actually in the PNP transistors we don't have electrons move, but the positive holes are moving. So this is a quasi-particle. And so how do they work? So there are bundles of magnitudes of energy, spin, charge, and effective mass. Effective mass. We've seen this term, effective mass. Effective mass is always used when you talk about groups of particles and have an average and then multiply it by the number. So this is not the free mass. We saw this. When we looked at how the electron moved through the crystal, we used the wave packet to get an equation that we could use to derive the Schrödinger equation. Then we said at some point, we have to forget about that it was a wave packet with several electrons. Now it's only one again. So let's replace effective mass by mass, and ta-da, here we have the Schrödinger equation, right? And this is effective mass. It's on purpose here because these are groups. They are collective dispersion reactions of particle groups to every energy behaving like a single particles. They are free of interactions. They are probabilistically determined by the n-particle Hamilton operator for solids. So the n-particle Hamilton operator for solids is a bit like the Hamiltonian we saw in quantum mechanics, They are in superposition states described by wave functions. They are indiscernible but differ according to spin. They are not generally localized, but localization can be approximated using detectors. They obey the law of conservation. So in a way, they are not as bad as the virtual particles, but they're still quite bad. Like the holes, the moving holes in the PNP transistor, right? And so, so they came about, they were invented in solid state physics so that we could still have mathematical models for solid state. Without them, we can't have mathematical models of solid state. Then we cannot build solid state devices like transistors.
So you say that they are electron holes. What does that mean?
Well, so an electron hole is when you have a metal, a pure metal that is electron saturated. That's a metal in which you know, so sodium is an electronegative metal. So sodium always wants to have one more electron. That's why sodium starts to burn. When you take sodium, as a pure sodium, it's kept in a watery solution. When you take it out in place, it will start spontaneously to burn. Have you seen it? It's quite cool, isn't it? And it happens because it's so thirsty for the electrons that it wants to take the electrons of the oxygen, and so it spontaneously burns. But so if you take now another metal that doesn't have this property and spike it with a bit of sodium, then you get electron holes, because the whole metal as a whole will have two little electrons. Now if you put a current on this, the electrons will start to move. So that's the holes thing. It's quite impressive.
So which electrons will start to move?
The holes will start to move.
The holes will
Yeah,
start to move.
yeah.
Which means, all that means, you're expressing it in an upside down way. All that means is that electrons are being deleted at certain places.
Yeah. It's, of course.
Much less
You could all,
sexy,
yeah,
isn't it?
yeah. I think so, but it's still, the point is, yes, I know, but basically what's happening is that a lack of charge is moving, and physicists call this a moving hole. I agree with you that it's a bit a charm, but it's still a quasi-particle, because it is not a moving particle, but you can interpret it as a moving electron as well, though that's more difficult. Here, but the Cooper pairs are really quasi-particles, because these are two, we know these are two electrons which behave along, which even add their spin together. So it's quite something. But I agree they are less bad than the virtual particles. Okay. Now, what are particles? I think physics cannot describe subatomic particles in a consistent way. That's also what Falkenburg says. So let's look again. The various particle models of modern physics cannot sustain the classic mereologic and causal aspects of particles anymore. In quantum mechanics can explain a single measurement. Quantum mechanics proves that particles can be entangled. Quantum field theory has abandoned particles altogether. Classical fields creates non-existing particle trajectories in the detectors. Group theory has mereological models only, and the operational view has the causal models only. So that's a real mess, isn't it? And so some physicists write, physics, I found a paper, physics has become a nightmare, they say, right? Because of this, because it's so inconsistent. And I think this is very, very remarkable, and it's something that has not at all trickled through into philosophy. So it's not really perceived by philosophers. Philosophers still kind of stuck. Philosophy's mathematics is stuck in pre-calculus, so just numbers and triangles and so on. That's all they can do. Yeah, it's a bit set theory, so that's a bit more modern, okay. But that's only thanks to Principia Mathematica, so there was a good advancement. But otherwise, so they're stuck there. And philosophy of physics seems to, with a few exceptions, Falkenburg method, stuck in the 1920s. It's quite, and one reason, of course, is that actually, so quantum mechanics, to understand quantum mechanics fully requires Hilbert spaces, which are bad, but group theory is much worse. So I cannot look forward to learn group theory properly to understand quantum field theory.
Simple group theory in mathematics is very easy.
No, yeah, but advanced group theory is difficult. Very difficult. So, what did we learn since Democritus? So, the classic concept of particles with mereologic and causal aspects traveling on closed trajectories in space and time is wrong.
So, let me just see if we got mereologic clear. So, in our book, we talk about minds. We say that minds are physical like everything else. So, there are only four forces operating. Ultimately, there are four forces operating on particles. But the particles are at such a small level of granularity that we can't see them or understand how they work, but they must be there. And how the particles relate to the mesoscopic events in the brain, which we call thinking or remembering and so on, is mariological in the sense that the parts of the brain which do the remembering are particles. Combinations of particles do their thing, and we experience that as thinking or remembering, and we can understand very little of what's going on down here for even more reasons than you would like. But that there are things going on up here, we know and understand already perfectly well. And so we try to have a non-reductivistic theory of the mind, which is based on physics, but without reducing mental experiences to physics in a way which would cancel the reality of the mental experiences. We want to hold on to the reality of mental experience. And mariological, as we use it in the book, is accompanied by causal, in the sense that also the causality which goes on inside the brain is to be understood at the level of particles, but it swims up through the mariology. Now, does that have anything at all to do with it?
Yeah, I mean, what we write in the book, I still agree with what I think it's right what we write in the book, because we believe, we know that it's true that quantum physics in the end converges to classical physics. And so therefore, when I say it's wrong, I mean it's wrong at the micro level. Field quanta cannot be isolated, so when I have a field, I cannot isolate anything of the field, but I can only see every field quantum in context. Unlike I can isolate the photon, but the photon is not a field quantum. Particles show non-local quantum entanglement. Quarks cannot be isolated at all, so quarks can only be indirectly observed in very high energy physics experiments. A trajectory in a detector is a series of quantum scatterings. A particle is not a single object, but a part in a whole with the propagation of a microscopic effect in a macroscopic environment. Only many measurements yield a quantum measurement result, and the causal relations can only be obtained from detectors using classical trajectory concepts. Subatomic particles are the classic-like propagation of effects in a classical environment. What the detector measures is a bundle of properties. Today's physics cannot give us a clear understanding of what particles are. The world must be made out of something, but we cannot see it. I think Democritus is still valid. That's my tough conclusion. We now recognize that we cannot answer the question, what are the basic components of matter using physics? Our best approach is to keep common sense for the mesoscopic world and to use the results of physics for engineering. Shut up and calculate. And that's my conclusion out of physics. It's a bit sobering, but then, you know, that's why I didn't become a physicist. So now I have confirmed it with a huge effort.
For the same reason, I did not become an epistemologist. And I did not become a moral philosopher, because epistemology and moral philosophy are all, what was your phrase? All something up.
Shut up and calculate.
Anyway.
But without epistemology, you know it, you couldn't do ontology. So you have epistemologic assumptions, Barry. You just hide them from the poor biologists and physicians, and you just don't tell them that they are there. It's like saying physics has no metaphysics. Of course you have metaphysical basic assumptions. Otherwise you couldn't do your ontology. Otherwise you couldn't say why the Italian ontology is wrong. Dolce. So there is still some epistemology that you're using.
Perfectly correct to the degree that it overlaps with BFO.
Yeah, but the rest that is wrong, you couldn't say it's wrong without epistemology. So you still do some epistemology.
No,
you just hide it.
I have knowledge.
Yeah, that means.
I have knowledge of epistemology.
He's cheating, you see. Anyhow, so this is very important, and this is the overall conclusion. So now, I am myself astonished that we could go through all of this material. So we still have a bit of time, and I would like to use this to show you Barry's and my latest. So I've shown you. Oh, wait, I'll show you one. So this is our view of. I showed it to you already on Saturday. This is our high-level view of ontology, how it's made up. So so we have an ontology of universals, and so with quasi-particles and virtual particles are really difficult to fit in here. That's why I want to put particles not in BFO, because then we get really problems with the quasi and the virtual particles, Barry. You see now why I want to, but basically these are, but a photon could also be here, yeah, but not in quantum field theory. That's why I prefer to have it also here. But basically we have here the reality model used in physics. It contains universals and a priori entities for mathematics, and then we have here ideal entities, and that I showed you already. And so this is a bit, now this Barry and I discussed today, we replace this with, I would say,
system and system element.
yeah, no, because we have even system relations, so we need here something else, but I would call this object of the physical observation or systems branch. We can still find the term, and under this, before the weight on the spring, we have then system relation, system and system entity, and the weight on the spring is a system entity, system is a system, and then system entity is the weight and the spring and the attachment of the spring, and the system relation is how they are bound together to form this. And then we have here the magnitude, and in these magnitudes, these are just examples, but in the magnitudes we have continuant magnitudes such as mass and time, and then we have also occurrence such as velocity, acceleration, or probability of location. So the quantum mechanic probability of location, the amplitude, is not a continuant, it's an occurrent. And so these are here. Then in the model we have then the model description and the mathematical part. And here we have, of course, the ontology of mathematics providing the way that we express the models mathematically. And this we saw already. So we have the constructive relation here, we have equality, inequality in the set constructor, we have the monadic entities, and by combining the monadic entities with the constructive relation, and there might still be a bit missing here, but these are only examples, we obtain structural entities, and there all the structural entities. That is all, most of what we have in mathematics are structural entities created using constructive relations applied to monadic entities. And now, so this is how our ontology will look. We have a physics and mathematics upper ontology, a physics, and then, for example, a quantum physics. So there will be others, right? There will be classical mechanics, electromechanics in general, theory of relativity, and quantum mechanics, and so on. So here we have quantum physics ontology, which contains quantum mechanics, quantum field theory, quantum electrodynamics.
Now, how are you going to formulate definitions for instance, particle in the quantum physics ontology?
So it can be done. To do it properly, we would say we have quantum physics ontology has a quantum mechanics ontology, a quantum electrodynamics ontology, and a quantum field theory ontology, and a solid state physics ontology. And the quasi-particle can only be found in the quantum solid state ontology. The particle, the boson, will be both in the quantum field theory, and then there's another view of the boson which is only the photon in electrodynamics, and so on. So this is how to do it. And then we have quantum engineering ontology, which describes quantum computing and quantum devices. And now I want to give you an example of a quantum magnetosensor based on the Josephson effect, which is a macroscopic quantum phenomenon. So this here is a supraconductor, which is a metal cap, very cool, so that it has new physics property. And here we have a magnetic flux, which is a magnetic field going through this supraconductor. And you see that this ring is interrupted, but here are Josephson contacts. What are these? So in the absence of any external magnetic field, the input current splits into the two branches equally. And the current can still, so if a small external magnetic field is applied to the superconducting loop, a screening current begins to circulate the loop that generates the magnetic field, cancelling the applied external flux, and creates an additional Josephson phase, which is proportional to this magnetic flux. So basically, if I put current on this, I have two currents, but if I put a magnetic field, I get a circulating current, which is called the Josephson effect, which is a quantum effect. And then this Josephson effect will create another magnetic field opposed to this magnetic field and cancel this magnetic field. And this of course is this opposed electric field which is called the Josephson phase, can be measured via these two contacts. So you get then a change in the conductance, a change in the phase of the electricity you measure, and this phase change shows you that as additional current, as a Josephson current, which is induced by the magnetic flux occurs, and that the Josephson and the electrons that cross this bridge are paired electrons. These are quasi-particles. Yeah, so they can jump. They make a quantum jump across this gap, and they can do this because they form these.
The gap is the shaded.
The gray, the darker gray is the gap, and they can jump across this because they behave. They have boson properties. They are fermions. They combine their spins, and suddenly they can light. They can now behave like a photon, fly over, and it's a real phenomenon, isn't it? So great.
What does it do?
It measures small magnetic fields. Very, very Gauss. No, what's the unit of the magnetic flux? Is it Gauss? No. So Gauss has the law of the magnetic flux, but Tesla. So it can measure femtotesla, very small magnetic fluxes. Now they build similar devices without superconductors to measure brane magnetic fluxes, and so they want to, by this, have something like a better MRI. Yeah, because it doesn't. These don't work with the Josephson principle. But this was the first. So this squid is a magnetosensor, and it's used in experimental physics to measure very, very tiny magnetic currents, and it's very sensitive, and it was developed in the 60s. So Josephson developed the theory in the early 60s, and then I think it was as a Bell Lab, they built the first real squids, and it is a very, very fascinating device. Now, how do we deal with this ontologically? So this is just not complete, it's just to give a feeling. So we have here a physics entity, we have a system. I've skipped several things, but it has a superconductor with a Josephson junction. So these are not ontologically right, they're not is-a relationships, but it doesn't matter for now. So we have a superconductor here somewhere in the system, with a Josephson junction, we have a squid. Then under magnitude we have things like the electric current, the electric potential, the magnetic flux, the quantum wave phase, and then and other magnitudes we need. So Josephson equations are really tough. So if you want to ontologize them, you have a lot of magnitudes to take into account. And then you have the model, you have a quantum mechanical model, you have the Schrödinger equation, you have a microscopic quantum phenomenon, and then you have the Josephson effect, which is a quantum electrodynamics phenomenon. So you need the Dirac equation as well, and so on. And so but you can see here that we can very clearly organize the knowledge and the data and information exchange for all quantum research and applications. And these models, of course, contain equations which come from the mathematics ontology. And so this is to give you a feeling of how this works. And now, now I would like to switch this off.
Yeah, I'll do.
Any questions where you want to see slides once more? Before?
Oh, no, I don't know how to do it with.
Let them ask the questions first. Don't switch it off yet, please.
So stuff like virtual particles,
Yeah.
quasi-particles, will they fit under system or under model?
Under system or?
Model.
So the virtual particle, so there would be system element, and there would this paired electron, the Josephson electron pair, would be a system element, right? So this is really bad because here it should be system element, system relation, and system. And so the system here is really, the squid is a system, right? And then, actually the squid is a type of superconductor. So this is actually an is-a relationship. But the Josephson junction is a part. So it would be a system element, and then there can be an is-part of relation that relates this to the squid. And the electron pair is indeed, and how do we get an electron pair? We get it at in superconducting substances. So if we cool a certain metal very to the almost 0 Kelvin, then we get the electron pairs. But the electron pairs only form and jump across the Josephson junction if there's a magnetic flux. And so this we would model a system element and then here we have all the magnitudes. Here we just have to be careful to properly distinguish between occurrence and continuance. Yeah, this which in quantum physics is more difficult than in classical physics, but it can be done. And then we have all the equations that are used to model what's going on in the SWIT. So that's how it's done. More questions? So and if you're interested in this, I mean, you told me, and you can very soon, Barry and I will have the paper about this, this ontology of physics and mathematics. It will have two examples. It will have the oscillator with dampening, force oscillator with dampening, so an oscillator, which is a classical mechanics thing, and then we'll have probably the photon pair, entangled photon pair as an example of quantum mechanics system. So then you can see, because that already teases out most of the ontological problems. So then we show how we set this ontologically, and then that's just a tiny beginning, but the principles are then set down, and then people like you are interested in ontology of physics can work on it. There's a huge work to be done, which is, I think, very fascinating.
So the idea is that the ontology in the BFO sense was developed in the wake of the Human Genome Project, when there were suddenly gigantic new bodies of data about genes and proteins and so forth, and also gigantic new kinds of devices that would do gene sequencing and so forth. And medical people did not understand any of these new sequence databases. They had somehow to find a way of unlocking the secrets of sequence data, and that problem was solved by creating ontologies using words and phrases which medical people and biologists could understand. And then hundreds of people are still spending their lives curating data and literature by using these ontologies to tag places where a given sequence or a given protein or a given chemical phenomenon is involved in some biological or medical outcome, such as disease or death. So they formed the community of what are called biocurators. Now there's an international society of biocuration. There are career tracks, there are degrees in biocuration. And when we started, there was none of that. The biocurator job was a completely new career. Now he and I are in the center of an attempt by a number of influential people to do the same thing for quantum physics. And then there'll be quantum physics curated. Maybe even curators for physics in general. We're going to start with quantum physics because it's still very small, and as we've seen, it's very simple. So we can do it, we hope, relatively quickly. But physics as a whole will be a much bigger challenge. Yes.
The Human Genome Project, the problem was a data problem.
So,
with the Human Genome Project, the problem was a data problem. But what is the problem? It doesn't seem like a data problem with quantum physics.
So,
I agree with you.
there are some differences of emphasis, but remember the Human Genome Project was not only a problem of data, it was also a problem of devices and new experimental capability, which turned out to have an immense significance for medicine. And I think there are quite neat analogies if you consider the devices which have been created and the implications for things like medicine.
But you know, you're right that the ontologies in biology were enabled the restructuring of big data masses to obtain to verify hypotheses using data. This is not the case here. Here it's more an administration effort to understand the landscape of quantum engineering. But it's not the case that data that could not previously be combined will be able to combine. So you are very right. And so this ability, so I gave a talk a couple of weeks ago at the ICBO conference, Biological Ontology, about where I showed how artificial intelligence algorithms now rely on these ontologies. I hope people understood it, or at least some understood it, and which is very impressive because now you can do things with AI that you can't do without the ontology. So your comment is absolutely perfect. It's really a big difference, but still there's a huge need because the bureaucrats don't understand anymore what they've spent their billions on, right? To put it in blunt words.
So the DOD would like to know what the DOD owns.
So you had another comment.
And
Sorry.
This is interesting. So what they want is an ontology of intellectual properties and an ontology potentially of device property, engineering property. The ontology of intellectual property is being created here in Buffalo. The ontology of all devices could potentially be created by your student. So we are communicating with the Undersecretary of Defense office in the country.
So I saw you, but he was first. No, he was first.
Yeah, so if there are two particles in a closed box, so without detection, there are two waves. I wonder if people want to split two particles by cutting, so can people do that? Because I guess it relates to the question of vagueness. So in some case of vagueness.
What is?
Vagueness.
Vagueness. Ah, vagueness.
So in some case of vagueness.
Ah, okay.
Vagueness is natural.
No, so okay, I see. So that's very good. So there is. So if the particles, first of all, we have to see what particles these are. Let's say these are two photons, and then you could build an apparatus to split the photons into two separate boxes. So you can basically, I don't know how this apparatus works, but you can take one photon of high energy and with spin 1 and split it into two quasi particles which are two photons of spin 1/2 each with opposite spin. And then you can use a Stern-Gerlach apparatus to filter them via the magnetic field, and then you have separated them. And then they are in two boxes and two waves, but they are now separated. So you can do that. You can use their physical properties, the MESQ properties, which were always on the top of all the tables I showed, to separate them. So they are not vague. But sorry.
So
That was the first
there's
example.
no filter, so even though you can, you tact once when it's in that position, when that, but then when you want to cut after the tacting, you can know where they are, right?
So you can, so no matter if it's one particle or two particles, you can know, according to the Heisenberg equation, with a certain probability where they are, you can even use a detector, know at a certain time point where exactly they were creating a signal, thereby losing their own existence. So, but then, for example, you don't know much about their momentum anymore, because if they have high energy, though, if you have then several of these interactions which create the bubble chamber, and then you can look at the trajectory and use classical physics to calculate their momentum. And so it's very indirect. So, I don't think vagueness is a proper word here. Let's look at another couple of particles. Let's look at hydrogen atom. Here we have a proton and an electron. You can also separate them just by heating them up. You just need to heat them up really high, and at say 1,000,000 degrees Celsius, they will be split. And actually, there is no probability the energy of the electron will be so bloody high, it can never go back to the proton.
Can you get to those levels of temperature?
Yes, the sun is doing it all the time, but also we can do it for a couple of seconds we do it when we do a nuclear fusion experiment, and also in nuclear fission, there is, of course, so when you have an atomic bomb, in the moment it explodes, there's so much energy that, of course, a lot of the material gets into plasma state. So you can do that. And that's another way of separating. So so it always depends on which particles you want to separate, but essentially down to the hadrons, which are protons and neutrons, you can always separate. But further you can't, so you can't separate the proton. So how do we know about quarks? Not by separating the proton, but by looking at the scattering pattern. So when we collide two hadrons at very, very high energy, we take a proton and make it go almost at the speed of light. Then we hit another, it goes into the chamber and hits another proton. Then by the scattering, you can conclude by the scattering properties what the other hadron contains. And now if the hadron is a neutron, it will lead to a different scattering pattern than the scattering pattern if it's a proton. And this is how we have developed the theory of the quarks. By seeing different scattering patterns. And then when we set up the equations to model the quarks, we realized that we need something to mediate their force that holds them together. So that's how the gluon was determined. And the gluon, and you can if you make the energy even higher and higher, you can change the scattering pattern so that it seems that they are pulled apart a little, the quarks. And this way you have now indirectly, you can then calculate what is the force that pulls, by which they are taken together, because it's a counter force. That's the third Newton's law. So you have the force that pulls them together, and you have now pulled them with certain energy, put them a bit apart. So now you can extrapolate the force that holds them together, and this is mediated by the gluon, and then you can give the gluon an energy that is the energy that holds them. That's how it works.
Okay. So in regular way, it's hard to do that.
That's why atomic fission is so dangerous. Yeah, because I mean, if you don't use it properly.
In some cases, veganism, it's about whether veganism is nature. In some cases, so it seems to me then there can be a cut line in just I think they may be related.
So for me, there is no vagueness in quantum mechanics.
So what's the smear then?
The smear is a probability distribution, but it's not vagueness. Vagueness is, for example, I have vagueness if I don't know the probability distribution. I know there is a probability distribution, but I have no equation. But here we have seen a great equation for the probability distribution, so I don't think there's vagueness. So vagueness is really a humanities concept.
Yeah, I just think of
No, I'm not.
No,
veganism is nature.
that's why epistemology is so ugly, because there are so many different ways in which vagueness can affect what people know and think.
Go ahead.
Okay. Yeah, no, I just want to say, my question is about whether veganism is nature. So if we really can't cut the two particles apart in a regular way, so maybe in some cases.
But high energy is a regular way. You see, when people criticize high energy physics, oh, this is so artificial. Physicists will look at the sun. Even once it was so funny. I was at the CERN. I was still a boy, and I was 11 or 12, and then they explained to me what they were doing. I said, "Isn't this a bit artificial? Can you learn something about nature?" And then one of them had an old style disc player for the LPs. You know, remember the LPs? So we put the LP on. It was the LP. I think I don't know what I think it's Let It Be or Abbey Road. He just played the song Here Comes the Sun. And then while it was playing, he was a bit crazy. He was explaining to me that the sun is a gigantic high energy reactor and so on. So I think there is no vagueness in nature. There is we can only model a small part of nature, of course, but vagueness does not apply. So you had the next question.
Yes, my question is more related back to ontology and intellectual property, less about physics. When you're talking about building these ontologies of intellectual properties, do you think that, this is so off topic but on topic for me, do you think that works of art will belong in these intellectual property ontologies?
Yeah, works of art have all kinds of different intellectual properties. You can own it, you can rent it, you can give it to someone else, you can give it to someone else under certain conditions. So when rich people lend their paintings to museums, they know that they're never going to get them back, but still there are certain conditions. So that's the kind of difference that the intellectual property ontology is about, the conditions under which people have intellectual property. So another difference is you can have intellectual property to own, you can have intellectual property to use without owning, and so on.
I read an article recently about several artists who have found that their art has been used to train AI to generate art.
Oh yeah.
And,
So go. I'm interested in that. Go ahead. Good. What?
Several artists across the U.S. have found, I forget the name of
they've used AI.
They're taking their art and inserting it into this
and
AI
then?
system to generate art that looks very much like their art but is not their art. So it made me wonder with these intellectual properties, because some people are trying to get their art back out of those systems.
He can answer more philosophically, but I can tell you the following. So the input is their intellectual property. The output is a mixed intellectual property of them and the creator of the AI algorithm. That's my view of it. And there is shared intellectual property, right? So if you have a patent filing, very often there are several engineers on it. So they share the intellectual property. It's nothing special. So you have an engineer sharing the intellectual property with an artist. Now, whether that's valuable art that's come out of it, that's a different question.
Right.
But I think it's just a simple case of standard shared intellectual property.
And I would say that whenever you have new technology, then you get questions like this,
Yes.
which we really don't know the answer to. And then,
But is this answer so difficult?
oh, maybe this is an easy one.
Yeah.
There have been other cases.
That's a much harder
Somebody
one.
has to sue somebody else, and then it goes to the court, and then the judge will say what the rule will be. And if no one appeals his ruling, then that ruling will count as the intellectual property regime for all future cases.
Well, unless the legislator says we have to make a new legislation, and that changes then the ruling. I mean, it's not only the judge.
Yeah, that's what happens in Europe. But
No, also here. All the time we have laws that are made also in England, I'm sorry to say it, since a few 100 centuries now, they have not only the Ting, or how it was called, where they have common law, I mean, we have a separation of legislation and jurisdiction also in England since quite a while. And so the legislators can also do a lot about this. So, and I think both legislation and jurisdiction are different ways how the society expresses how it deals with such phenomena, right? But in the Anglo-Saxon world, most of the time the judges come first, whereas in Europe often the legislator comes first. That's a difference. So that's a big difference. So it has been, with the cultural erosion of continental Europe, this has changed to more to the English model.
Neither of them are experts.
No, yeah. And so that's another question. When you realize, when you then are called to the legislator, I haven't been called to a court. No, it's not true. I've been called to a court once as an expert, and once to a major legislator. And when you then realize they don't understand anything, and then they should decide. And actually, with the judge, it was a little bit better, but with the legislators, they didn't know. So there were 5 experts there who had to give expertises which were competing. I was in the minority position, and at some point I realized that the other 4 experts, they had all degrees in humanities. None of them could define an electron. And it was about renewable energy, and then I said at some point, but gentlemen, can any one of you define an electron? Is anyone here that they couldn't? And then I said to the legislators, this was the Ausschuss, Landtagsausschuss. So do you realize you want to listen to my opponents here who can't define an electron? This is about energy. There was an awkward silence.
What did the legislators say?
In the end, they voted, and the CDU and AfD and FDP voted for my minority opinion, but the Greens and the SPD voted for the nonsense, which was
The nonsense.
yeah, which was in contradiction to the laws of physics. But it is on. But there you see, but they were morally superior. So that's what at the end made the decision, in their own eyes. Anyhow. So I think I think we have done enough. So the main thing I wanted to show that is not on the slides is how this is more fine-grained. Yeah, and so to repeat it, under model we will have a verbal part of the model, graphical part of the model, and there are 2 types of graphical models. There is a depiction of the situation, and there is the geometric figure. We've seen examples of both. Geometric figures is when you suddenly see cosine and sine and so on, and people use this to derive the equations. These are geometric figures, and graphical are more like, this is how this one here was a graphical one. So this is a different, right? So this is also graphical model, but that's another type. So this is a graphical model, and this is a graphical model, but they are not the non-geometric ones, but the functional ones, and then there's yet another one. This is basically a more formal version of this, and then there are the ones which are completely geometrical, and the third branch, which is here, is their mathematical model. So these will be 3 branches on the model. Here we will have 2 branches, namely continuant magnitude and occurrent magnitude. So one is an entity characteristic, the other is a process characteristic. Velocity is a process characteristic, and weight or mass or mole are entity characteristics. And then here I already saw. That's what I wanted to add. And then, so to speak, to the left and the right, we have BFO and mathematics ontology, and there will be, and the reason why it hasn't been done so far is that I think people don't understand how physics works epistemologically. So we also here need some epistemology to understand what the physicists do. We need to understand that the physicists
Have more knowledge of physics.
Yeah. Okay. So I think this was it. I hope. Any more questions? Yes.
Do you think this is ready to be presented to the
I did this already.
how did you react?
Oh, they said you have understood quite a lot about quantum field theory. They are quite so I just called a couple of days before. I called my uncle. He's a theoretical physicist who worked his whole life at CERN. He's a really distinguished man, very good, he's quantum field theoretician. And so I told him what my understanding was, and they said, oh, you should read. He gave me a couple of books to read so that I can understand more details, but he said the overall conclusions are clear, that the more we do experiments, the less we understand what matter makes up matter, and that he also prefers to go back to the good old Bohr model if he wants to do chemistry. So when you think about how chemical bonds are made, you think of the outer high energy shell of the atom, and that creates all the chemical interactions, and then you can use quantum mechanics to model this. And so, but he says at the same time, I know that this is just one model, and if I look at quantum physics, I cannot use this model anymore, but I just use the model that in physics that I need for my context. So in the context of explaining chemical bonds, I need the good old quantum mechanics. In the context of understanding single photon interactions, like the one I showed on the Feynman diagram, I need the quantum electrodynamics, and if I want to understand matter, solid state physics, I need to use quantum field theory and so on. So they are very much aware of this, and also Feynman is aware of this. He says in chapter 9 of volume 2, he describes condensers, and then a cloud is a bit like a condenser, right? So when you have a tempest, sorry, not a tempest, what is it called? A storm with thunder and lightning. Basically, the surface of the Earth or the sea is positively charged because in natural processes the surface of the Earth and the sea lose electrons. So these electrons go into the atmosphere, and so they accumulate there, and so there's then a potential difference. And the lightning, and we have at every moment we have 7,000 lightnings per hour on each day, each hour, somewhere on Earth. They're needed to put the electrons back to reduce the potential difference that is building up permanently, and so the lightning goes down and basically brings electrons back to the Earth. However, the way that the cloud and the Earth interact and how the charges are distributed, we can't explain at all. There are no models for this because in detail they're in the cloud. There are regions of positive charge and others of negative charge. They interact somehow. There's nobody who can explain this. And then he said, so now if we take a break from our highly idealized models and look at real natures, we realize we have no clue how it works. So the good physicists are aware of all of this, but that doesn't lead them to relativism, just to modesty. And so that's why usually with physicists I get on much better than with, for example, computer scientists who believe they can build AI systems. Yeah, because they don't understand the mathematics and physics. And so they are over-optimistic. And so the feedback I'm getting is positive. I mean, my uncle says, oh, Jobs, I expected you to understand how physics works. That's what he said. So I mean, before I would present this to physicists to be really proof against aggressive physicists, I would now, my next task is to work myself through quantum field theory, which I haven't done properly. So now I've worked myself only through
solid state.
Yeah, that is part of it. Yeah, and then I so to deal with non-friendly physicists, I would have to do this first, but then after that, I feel ready for them as well. Good. So I hope. Oh, yeah.
I'm not physics, so I understand quantum is non-unity and not holism. So I think I'm confused about what is the function of the wave and energy in the quantum state. Can you explain more about it?
Yeah. So the wave, the Schrödinger equation is a wave function that describes the propagation of a wave, like the sound wave function that describes how the sound I make is also a wave. It's a sound wave, and it reaches your ear and transmits and basically it transmits the energy that. So I put energy when I speak. I put waves of energy into the air. that propagate. Basically, it's electromagnetism because I put some molecules move, they hit other molecules, they make these molecules move, which make other molecules move until this reaches your ear. And that works like a wave, right? And so if I put a block of metal I have a candlelight here and I suspend a block of metal above it, the heat will also propagate in the block of metal in waves, and if I put my hand on it, after a while I will feel the heat arriving there. That's the Fourier equation, it's also a wave equation. The Schrödinger equation is nothing but, and in both cases it deals with energy. The first time it's the energy that my voice creates, second time it's the energy of the candlelight that propagates, and it's just also here, the Schrödinger equation just describes the energy which makes the propagation of the particles. Yeah, it's still just, that's the energy in it.
So you mean that we can measure energy through the wave of function?
Yeah, the Schrödinger equation expresses the movement of a particle using an energy matrix, which is Hamiltonian, and it describes the states of energy. Hallo David, ich bin noch in meiner Vorlesung, ich bin gleich fertig, dann rufe ich dich zurück. Hast du gehört? Bis gleich. Sorry, that was from a call from Germany. Sometimes they don't realize what time it is here. So
couldn't you say that the split experiment just converts the particle into an energy wave?
It doesn't convert it. The particle is an energy wave when it is emitted from its source. The split experiment, if I close one slit and make a measurement, then this wave behaves like a particle. Because I obtain the distribution I would obtain from many particles being shot through the slit.
So besides our presentation of the last few days, is there a plan to, I mean, as someone who appreciates your level of being able to explain it, is there somewhere I can go to understand? I mean, I'm going to go to Feynman, I'm going to go to Griffith and Omnes, but like you said, there's very mathematical and everything. Do you have any plan to make the presentation we've just had into any sort of like paper or?
My plan. So first of all, to get a good understanding, Feynman is the best way to do it, and Feynman is actually very cool because throughout this book he introduces all the mathematics he needs, and he introduces them without proofs, without all the burden that a typical mathematician carries around. But if you read the book carefully and use to remind you and to help your memory a collection of mathematical equations, like how is sine and cosine defined, how's the E function defined, then you can work yourself through the book. Yeah, so and then you can understand a lot. Yes, I'm Barry and I write papers about ontology of physics, and I want to write a book about my view, philosophy of quantum physics.
And so that would include this last few, the particle.
Yeah, it will probably build up a bit differently from the lecture, but it would contain all quantum theories and do the conclusions more systematically. And I also saw that this slide is now that I wrote earlier is now outdated a bit because I wrote it earlier before writing the other part, and I would harmonize this and so on. So I should probably change this slide before you put the version online. But I don't plan to do so. But the book will, I don't know to what extent it will be didactic. I don't know. It's very, very hard to write a didactic book about quantum mechanics. Many people have done it, and I don't want to do another one. So I want to do a book about its philosophical implications.
So it's going to be a competition for modeling. Philosophers have
Yes.
tried to write about quantum mechanics, but they don't know the mathematics. And modeling probably knows the physics, but he doesn't know all of the things that York knows. So he's going to write a book which will show modeling to be wrong.
Yeah, no, I mean, but probably, I mean, as I showed, the problem that even if we use the most elegant way of modeling quantum mechanics, and that was only the Schrödinger equation, still we have this big problem of non-unity. So the contradiction between quantum mechanics and our common worldview don't go away, even with omnes. But that looks like a small problem if you add the problems introduced by quantum field theory. Yeah, because it's very interesting. The more you mathematize physics, so when you look at Lagrange, he created a mathematical, very elegant, Lagrange and Hamilton, very elegant mathematical views of classical mechanics. But they did not dissolve yet the common sense nature, because the common sense nature is perfectly conserved in their mathematical formulations. The same is true for Maxwell, who created beautiful equations to explain electrostatics and electrodynamics. But then when you, with the event of quantum mechanics, you start to dissolve the common sense more and more and more, and now with quantum field theory, the discrepancy has become unbearable, because it's even much, much worse than what you have in plain quantum mechanics. And that's quite problematic, and that comes from the very, very heavy mathematical abstraction, and because the mathematics are independent of the real world. And so the more you put everything into mathematics, the harder it gets to understand this from a common sense perspective. That's how physics went, and that's very dangerous, because we have in the humanities, we have already had a dissolution of common sense since the middle of the 19th century. Since Marx, Stirner, Feuerbach, they started to dissolve our common sense view of the world. Yes, all terrible Germans, I must admit it. Yeah, and they actually, and then even Heidegger was even worse. So the Germans brought all the evil to the modern thinking, really, and all the French guys like Derrida and Foucault, they are just Heideggerians. Yeah, so it's really terrible. Nietzsche is also part of them, and so and so then we have this in the humanities. They are completely destroyed now. And now you look at physics, oh yeah, but we are still physics. No, there are also lunatics now in physics, yeah, who say, and so they also undermine realism. So it's kind of tough. Okay, but still we continue with our realism. We believe in it. and it was a big pleasure to give this course. I hope you had some fun and learned something, and I hope to see you next year, some of you. Thank you very much.
So there are still 2 people who didn't send me their titles for next week. So whoever you are, send me your title. And you can find out whether you are one of those people by looking at the program, the wiki. Sorry, go ahead.
Yeah, I have a question about the
Some fiat boundaries are vague. Some fiat boundaries are crystal. So really, it doesn't get rid of vagueness. It just allows the conceptualization.
Barry, I go to the restroom and then I pick you up.
Barry?
Yes.
Next week is presentations, correct?
Yeah.
And do you want to just use one laptop for presentations, or like
No, we've got.
What's the closest way to the nearest restroom? I'm following you. Very good. So you know your way better here than I do.
Someone has to know their way, right? Right here.
Oh, thank you.